So it's a great pleasure and honor to speak in a conference of my scientific hero, John von Neumann. The topic is a topic in stochastic game theory, which is called stochastic games, and later it will be clear why I choose this particular topic. And it's always good to start a talk with an outline, because when I talk on the outline, I give highlights of few points that will be mentioned, and usually we are used to the fact that we don't always go all the way to the end, so at least you would know what we are missing. So von Neumann was a founding father of many scientific disciplines. One of them is definitely game theory. Yes. And he basically contributed in three different connecting areas in game theory. Often, nowadays, people are either handling the first or the second or the third. And those three topics were strategic games, which were studied and introduced in von Neumann's paper in 1928. Then cooperative games, which are in the book by von Neumann and Morgenstern, 1944. And another component there is the issue of cooperative strategic games, basically to try to incorporate those two theories together to start from the strategic games, moving to the cooperative game, and then making the analysis of these games. The presentation today is a journey from von Neumann's 1928 paper, which marked the birth of the mathematical theory of games to the development of the modern theory of stochastic game. So obviously, I say the mathematical theory of games, but this mathematical theory of games that he initiated was the foundation of many applicable future works. And if we think of the impact of his work and the follow-up, there are at least 12 people that got the Nobel Prize for work in game theory, in economics, the Nobel Prize in economics. So there are few instances of earlier work that used game theory. One is Cournot, 1938, Zermelo from 1913, which I'll describe explicitly what Zermelo did, and Borel, 1921, which I may mention something, but let's just say that he was trying to do what von Neumann did in his paper 1928, but basically he conjectured that something is false, which von Neumann proved it's correct. So we will focus in this talk only on follow-ups of his work on the minimax theorem from 1928. And in this work, he basically did three conceptual and technical contributions. One is defining what is a game. Yes. He knew that people are playing poker, chess, soccer, competition between firms, etc. But to formalize it as a mathematical concept, what is a game? Tell me the story. The story of the game could be highly complicated, but make out of it a simple thing. And then once you get into this fact of what is a game, you understand what it is, you understand what is a strategy in a game. Yes? A strategy of a game is a method of how to play the game. Any instances, what you know, what you don't know, take an action as a function of what evolved so far in the game. And then come a brilliant idea that says the way that we are going to analyze this game is basically we could think a priori, what is a strategy? There is a strategy of each player, and if we pick a strategy of each player, then we could follow up and see what will be the outcome of the game. The outcome could be probabilistic because there might be some chance moves, but we could compute it. And then we can model the entire situation as a kind of a simultaneous move game where each player is picking up his strategy. It's worth mentioning that in Borel had this intuition as well, but he has summarized it in only one sentence, and it's not clear, but he didn't define formally what's a game, so obviously the birth of this theorem is for Neumann 1928 paper. So this paper was called On the Theory of Games of Strategy, and it contains just this single paper, I say there are 3 parts of his contribution, 4 fundamental contributions. The first is the description of a game of strategy, including who are the players. We'll see that there could be here some confusion from our intuition as laymen. Second, so this first one described many games like chess, poker, Kriegspiel. Probably you don't know what's Kriegspiel, but it's a very interesting game, strategy game, word playing, and as well as a competition among firms, nations, animals, and the various auction mechanisms. And nowadays auctions take such a large part in the real life days that people don't know that there are auctions in trillions of dollars almost daily. The second is the definition of a strategy of a player in a game. So you describe the game, the formal thing, and then you have to define what is a strategy. The third is the description of the game of strategy as a one-shot simultaneous move game. So you have to think of it as before and. Each one puts in a box his strategy, a referee looks on the strategies and now starts to play and follow the game according to this strategy. The fourth is the minimax theorem. Once you have this formalization, then you have what's called the minimax theorem. The minimax theorem is extremely important in economics, but served also as a mathematical tool to solve few old open problems later in the days. But one has to think of it in a smart way. So I said this is the minimax theorem of von Neumann, this paper, where we will start. Then I'll move to stochastic games. These games were introduced by the first that I mentioned here, Nobel Prize winner, Shapley, in '53, and this was a paper that was communicated to the proceeding of the National Academy of Science by von Neumann. I think it's the first paper that von Neumann communicated in game theory after his work to the proceeding of the National Academy of Science. And I will try to describe what is a stochastic game. In the first part, where I speak about the minimax theorem, I would build the minimax theorem, the story behind the minimax theorem, in a format that will be suitable for my definition of what is a stochastic game. So it will follow similar lines, so it will be easier to follow. Then the first paper of Shapley was proving that the discounted stochastic game, and proved there an existence of a min-max theorem for that particular game. I should say a priori that in the initial theory of von Neumann of the minimax theorem and the development, all the games were finite. So they were eventually finitely many strategies. In this theory of stochastic game, we will see that there are infinitely many strategies, even though the game itself could be described by finitely many parameters. So the finiteness comes from the description of the game, but the strategy themselves becomes infinite strategies. Then I will illustrate examples of stochastic games. These examples will be specially tailored for also for explaining what is the game and also to explain to mathematicians some of the difficulties that arise in stochastic games. Then I will present a result about the existence of the undiscounted value in stochastic game. So in general, in the stochastic game, the play of the game results in a sequence of payoffs to each player. So the player gets a sequence of payoffs. And the question is, you look on the entire game, what is the payoff of the entire game? So if you look on the payoff of the entire game as a long-run average of the payoffs in the one games, that's called the undiscounted game. And the issue whether there exists a value for this game, a minimax theorem for this game, was open for quite some time and settled eventually by Mertens and myself. Then we will switch to the Nash equilibrium theorem, Nash 51. A theorem, a very short paper, a masterpiece. Nash got the Nobel Prize in economics just essentially for this paper. There is almost no paper in economic theory nowadays that doesn't use the concept of the Nash equilibrium theorem. And if we go back to von Neumann, I didn't meet von Neumann, but I was a good close friend to Nash. And so the story from Nash, when he came with the theorem to von Neumann and he showed him, he said, oh, that's a fixed point generalization of the min-max theorem. So immediately I've seen, when he explained him the result, the proof of the result and what is the meaning, but he didn't formalize that in his own paper studying competitive games. And then we will move, since we have the concept of an equilibrium, we'll describe what is a non-zero-sum stochastic game. So in a zero-sum, in a competitive stochastic game, one player maximizes something, and player two is the adversary who tries to minimize this payoff. And then we will define the undiscounted equilibrium in this type of game. And for the mathematicians in the audience or in the online, in honor of another great Hungarian mathematician, Paul Erdős, who used to pose up open problem and offer prices for this problem. So one of the objectives of this talk is to pose an open problem about undiscounted equilibrium in stochastic game, for which I offered already many years ago a prize, which is a dinner in any restaurant in the world, including transportation, if the solution is positive, and a dinner without transportation if the solution is negative. So you are all invited to work on this thing. And I would say that the initial problem that I posed, the one that I'll pose here, I wouldn't have enough time to describe the general problem, but this is a watered-down version, but still I would give these prices for these watered-down versions that I am posing here. And then we will close, if there will be time, to discuss on three different theories of stochastic game: the asymptotic, uniform, and robust theories of stochastic game. The asymptotic value, a theory developed initially by Bewley and Kohlberg, which looks on the solution of the game. You have a solution of the game, and you try to see there will be various ways of evaluating streams of payoffs, and you want to see if when the players become more patient and more patient, does the solution converge to a limit? This is the Bewley and Kohlberg result there. The uniform value, which was initiated by the work of Mertens and mine, was not only to show that these values converge, but that there is one single strategy that a player could utilize simultaneously, optimizing simultaneously for all the stochastic games with sufficiently patient players. And the final thing is the robust solution of finite stochastic game that tried to show how, in a family of stochastic game, you could vary your optimization in a continuous way, in a uniformly continuous way. So let's go back to the first part. For Neumann, somebody said here that he lived 52 years in one of the seminars, but my computation is 54, right? I think in one of the lectures there was. So he's the father of game theory, and as I said, is the minimax theorem, the competitive, in 1928, and then the two other subjects by von Neumann together with Morgenstern, which I was hoping to hear the quote from Morgenstern on that, so I'll get it privately later, what he said about him on his view. Another important Hungarian-American contributor to this theory is Arsani, who also got the Nobel Prize for his contributions in game theory. So we already mentioned two. I wouldn't mention all the 12, but we have those two. And as I remember that this contribution has three components: what is a game, what is a strategy, and the minimax theorem. And when we describe what is a game, in particular, what is a player in a game? Okay? So let's look on a few examples of players. Okay, you have at least two great Hungarian chess players, Judith Polgar and Lajos Portis, who are still alive. I think there is one even greater chess player that is no longer alive from the earlier 20th century. And I'll speak in a minute about the work of Zermelo on chess. But a player in chess, in the game of chess, is not one of these players. Yes? A player is the position. You are white, and you look what white in chess could do, the strategies of white. It is true that in game theory there is room to incorporate also the analysis of games in which you incorporate the same game of chess. You look at it as a family of several games with different abilities of the players, and the question is how to formalize what are different abilities of the players and to classify it as a family of games. Another game that I like is soccer. And one of the Hungarian famous players in soccer, probably the greatest of all times, is Puskás. Yes. And again, the game of soccer is also a game, but it's more difficult in a sense to formalize it without taking into account abilities of the players. And as we will formalize other games, that we think of it as sequence of games, so a sequence of stages by which there is one first move, second move, and so on. It's a kind of a game in continuous time, because all the time there are outcomes of actions of the players. So there will be a small reference to continuous time games later, but again, soccer will not be covered by what I'm speaking today. So the first kind of mathematical theorem in game theory was Zermelo, that he delivered the talk in the 1912 Congress of Mathematics, and he proved that in the game of chess, either white can force a win. So either white has some strategy. You could write instructions for white that will force that he wins the game, or black can force a win, or each one could force a draw. By the way, it's an interesting question. Nobody knows nowadays, even though there is a feeling that the black can force a win is not possible, because from experience people are used to the fact that white has a slight advantage. But nobody could, so far, nobody can prove it, this theorem, that this possibility that black can force a win is not true. Okay, so I will essentially almost prove you this theorem of Zermelo. And I will state a more general theorem, which is a win-loss game of perfect information. So we look on a game, on a result on games that generalizes that Zermelo's theorem follows from it. And we look on sequential games. First stage, player one chooses a move A1, and thereafter player 2 chooses a move B1. In the kth stage of the game, player 1 chooses AK, and player 2 chooses BK. So now we know what the game is progressing. So a play of the game will be a sequence of moves, A1, B1 up to AN, BN if it's an end-stage game. And then we define when player 1 wins. So I said a sequential game with perfect information. In a moment, I'll explain the concept of perfect information. And then there are a sequence of moves, plays of game, by which one wins. And otherwise, player 2 wins. The game is of perfect information if before each of his choices of the player, he observes all past moves. So he knows what happened so far. And now comes a concept which is important. The pure strategy of a player in such a game, since he knows everything in the past, is what he does in his kth move as a function of all past moves. And the theorem, the determinacy of games of perfect information without chance moves, here there were no chance moves like in chess. In poker or in other games there will be chance move, that either player 1 has a pure strategy that guarantees that player 1 wins, or player 2 has a strategy that guarantees that 2 wins. And for the mathematicians, you have a trivial proof of this theorem, because it follows from the fact that the logical negation of the formal quantifier statement that player 1 has a winning strategy is the formal quantifier statement that player 2 has a winning strategy. Because what is the formal statement that player 1 has a winning strategy? That there exists a first move, such that for any reply of player 2, there exists a second move of player 1, such that for every, and so on, such that the sequence is a win for player 1. Isn't that set W? What is the negation of this statement, logically? If there doesn't exist a first move for player 1, it means that for every move of player 1, there exists a move of player 2 such that this is not in W. So if you look on it from the logical statement, and for the mathematicians, it's people are making these statements automatically in all their logical arguments, but they never prove it. So you have to prove it by induction. Yes? Okay? Now let me give an example of matching pennies, a simultaneous move game, because we say that eventually translate everything to a simultaneous move game. So let's look on one simultaneous move game, which is described by this matrix. Player 1, his strategy are either top or bottom. Player 2 strategies are either left or right. And the entry in the matrix specifies what is the payoff to player 1. Namely, if he wins or loses. So this is not a game of perfect information, because you don't observe first the move of the other player before you take your move. It's simultaneous moves. And you could see that in this game, if player 1 takes the first move, all that he can guarantee is a payoff of 0. And if player 2 is the first one to take the move, all he guarantees player 1 could force a win. So in symbols, for the mathematicians, I write it here. Yes? The max-min, maximizing over the strategy of player 1, minimizing over the strategy of player 2. The pure strategy, this gives 0. Player 1 cannot force a win. But if you minimize by a strategy of player 2, and then look on the reply of player 1, the min-max is 1. So if player 2 would have moved first, let's look on an end-stage simultaneous move games. Before it was one move. So the first, player 1 chooses A1 and B1 simultaneously. And thereafter, there is a chance move. Chance makes a move C1. The kth stage, player 1 takes an action AK and BK, and player 2 BK simultaneously, and then nature chooses CK. So the play of the game, first of all, the distribution of CK of nature, when I say nature, means that its distribution is determined by everything that followed so far in the game. It's not a choice of nature, it's dictated by the rules. A play of the game is a sequence of moves of of players and nature. And again, player 1 wins if that sequence is in some specific winning strategy. So W is a subset of the place. A place includes here also the moves of nature. And the game is finite if the number of moves at each stage is finite. And for Neumann's result 1928 is that any finite simultaneous move game has a value V, namely player 1 as a mixed strategy. So not a pure strategy as before that it specifies all the rules. It disguises what it takes as his first move. It takes a probability distribution, which is called a mixed strategy, that guarantees that he wins with probability at least V, and player 2 as a mixed strategy that guarantees that player 1 will win with probability at most V, and therefore V is called the minimax value of the game. So this can be generalized to matrix game. So player 1, the pure strategies are set A, the pure strategies of player 2 are B, and then we have a real valued function as a result of the choice of the two pure actions A and B. And the players, we think of it as playing simultaneously. And one could say that any such game, I wrote a general payoff, but it is equivalent to a win-loss game with a chance moves, because if the payoff is 1/2, you could interpret it as nature decides if the payoff is 1 with probability 1/2 or 0 with probability 1/2. And the minimax theorem of Neumann states that any finite matrix game has a value V, and each player has an optimal strategy. Namely, there exists a number V, called the minimax value of the game. Player 1 has a mixed strategy, called an optimal strategy, that guarantees that the expectation of his payoff is at least V, no matter what is the strategy of player 2. And player 2 has a mixed strategy called optimal strategy of player 2 that guarantees that the expectation of the payoff of player 1 is at most V, no matter what is the strategy that player 1 takes. Now let's move to the second part, which is stochastic games. And in my description of the simultaneous move games with chance moves were a kind of a preparation for this type of model. So this was a paper by Shapley, 53, communicated by von Neumann. So what is a two-person zero-sum stochastic game? It's a multi-stage game. The environment or position or state, the formal language is state, changes from one stage to the next stage. If you think of fighting, of utilizing natural resources, if you use some of the resources, you affect the situation of next time. If you look on models of global warming, then, and you try to optimize maybe the average of the GNP of the world, you know that if you make too much optimization, you may damage the future time. And therefore, there is a situation that changes from time to time. In each stage, the players face a matrix game. So I'm going back now to the two-person zero-sum, so it's easy to illustrate. So in each state, you think of a matrix game. But the current state and the actions of the players at this stage specify the payoff that the player gets. The stochastic game payoff is a weighted in the entire game. We say you get stages, is a kind of a weighted average of the stage payoffs, or a limit of such weighted, like I said before, the long-run average of this payoff. Therefore, in a stochastic game, in all the applications, and also in the mathematical theory of it, the choice of action at each stage is guided by two often conflicting objectives. On the one hand, you want to maximize the payoff that you get today in this period, but on the other hand, you want to guarantee that you are moving to the next state that is favorable for you. A pair of strategies like before of player 1 and player 2 define a probability distribution over place of, and therefore also over the streams of payoffs. And the objective of each player depends on his valuation of the streams of payoffs. Player 1 desires to maximize his valuation of the stream of payoffs, and player 2, who is the adversary of player 1, tries to minimize it. So the minimax theorem for discounted stochastic game. So in the first paper of Shapley, slightly more general, but at least if you look on the game, it generates a sequence of payoff G1 in period 1, G2 in period 2, and so on. And you evaluate the stream as often is classical by economic theorists to take the discount, the present value of it, to weigh the different payoffs GT at period T by this weight. The sum of the weights is 1. You always take sum of the weights of 1 so that a constant payoff is valued as this constant payoff. And Shapley's 53 paper shows that any two zero-sum R-discounted stochastic game with finitely many states and actions as a value, which we'll call VR for later notation, and each player has stationary optimal strategies. The fact stationary strategy means that you don't have to look on everything that happened so far in the game. You just have to look on the present situation. And the reason is that if you look on this payoff function, if you know what happened in the first stages, 5 stages of the game, from here onward, you are trying to optimize, again, a multiple of such things. So you can forget the history. I would already right now say that in the long run average, this property of stationary or disregarding the history is impossible. So let me quickly describe to you one such stochastic game. Called the MIG match, was introduced by Gillette in '57 and solved by Blackwell and Ferguson in the late '60s. So I say there are states, and in each state there is a matrix game. So the two bottom one are trivial matrix games, a payoff of 0, a payoff of 1. You could interpret it winning or losing in this period. And the top payoff is, the top matrix is like the matching pennies. But now I have to decide what happens to the transitions. What is the next state? So if we are in each one of those bottom two states, yes, we are basically staying there. There is no move out. These are kind of absorbing states. But if we are on the top matrix, if we play that box, then we move to this state. If we play that box, we move to this space. And if we play the bottom, the top row, we play again this game. How to optimize this if you worry about the long-term averages of the game? Not a trivial issue. It's took a couple of years since the statement of this problem for its solution. In the undiscounted player, one maximizes the frequency of winning rounds, the rounds by which the payoff is 1. I'll show you another game very quickly, which is the Bewley and Colbert game, 1976, which has slightly twist on it. So you see that in this game, you have 4 different matrix games, 4 different positions. In each one, the payoff is specified. So in this game, all the fight will be for the next position, not for the payoff, because you know that in each of these states, you'll get the payoff. In the bottom one, you come back. From these boxes, you are going here. From those boxes, you are staying in the same game. If you play this box or this box, you stay in the same matrix game. And in all other cases, you are switching stages. Again, when they posed it, it was unclear how to play this game. What is the value of this game if you are playing it for infinitely many rounds and you try to maximize the expected rounds that you are winning the game. So strategies in the stochastic games are exactly like strategies in the simultaneous move games with chance moves, because what we have here is simultaneous moves and chance moves. So you have the concept of a play of the game, which is the initial state, the actions of the two players, the next state that nature chooses according to some fixed probability. So this is a play. And a strategy specifies, the player specifies the action as a function of everything that in the past. So we are looking here on case that you remember all the past. So you get a sequence of stage payoffs. And so the first the solution for the general finite stochastic game is 2-person zero-sum was in a paper of Mertens and myself that we proved that any 2-person zero-sum undiscounted, so we look on the long-run average stochastic game with finitely many states and action as a value v, namely, and let me elaborate, what does it mean? There is a number v, like in the minimax theorem, and for every epsilon, each player has epsilon optimal strategies. There is no chance here to get optimal strategies. Only you could maximize within an epsilon. And this means that if you take the limit superior, the long-run average, if you want to take the limit inferior, for mathematicians you have to be specific. So look on the limit superior. Player 1 has a strategy that guarantees that the expectation of this long-run average is at least v minus epsilon, no matter what is the strategy of player 2. And similarly, player 2 has a strategy, a mixed strategy, that guarantees that the expectation of this payoff is no more than v plus epsilon, no matter what the strategy of player 1 is. And I already indicated before, but let me repeat, it's an important story here. Obviously, if you played 10 periods of the game, all that matters is the future payoffs, because you look on the long-run average. So it looks that if you should have been able to play optimally or approximate optimally without looking back. This is not the case. It's impossible. You must look on the back. And if you remember from the Bible, the paros strategy is if you have 7 years, you will have 7 years with good productivity, be careful, save some for the next years that will be with low probability. So you have to look, your actions is not stationary, is not just time dependent. You look what happened in the past. And indeed, the solution of this theorem was a kind of a similarity to what the Federal Reserve in the US is doing. It's basically adjusting interest rates according to the performance of the economy. So when they see that people are investing too much now, and you think it's too much investment, take care of now, they increase the interest rate. Say, careful, today is more important than tomorrow. And basically the solution of that is a very careful play with interest rates, with a discount factor, that you compute that discount factor as a function of what happened in the past, so like the Faro strategies, and you play optimally as if you are in an R-discounted game. So let's move now to, how much time are you? 8? It's 45. I started 8 minutes, okay. So quickly, I want to come to the open problem. So Nash, 1928 to 2015, is the only person who has been awarded both the Nobel Prize in economics and the Abel Prize in mathematics. And obviously, if von Neumann would have lived slightly longer, he will be in the same category. Yes. And as mentioned before, also winning all the Nobel Prizes in a few other areas. So Nash equilibrium theorem, multi-player, so the same as two players competition. You look on each player as his own payoff function, so not as before, as one maximizes, the other one minimizes. And the Nash equilibrium is a list of strategies that no player can benefit from unilateral deviation. And the theorem of Nash says that a game with finitely many players and pure strategy has a Nash equilibrium. Namely, there is a list of mixed strategies, X star I for each player, such that if only player I decides to switch, it doesn't gain anything. So no unilateral deviation generates thing. Multiplayer non-zero-sum games is the trivial generalization of the previous two-person competitive game. The state changes from stage to stage. In each stage, the players face a multiplayer non-zero-sum game. the current state and action profile of the players determine the payoff in this stage, and the probability distribution to the next stage. A list of strategies of the players define a probability distribution over plays of the stream and over streams of payoffs. And each player desires to maximize his own valuation of the stream of his payoffs. So a play defines a stream of stage payoff. Okay, we could run on that. And let's define what is the undiscounted equilibrium in finite non-zero sum stochastic game. So the number of players is finite, the number of states is finite, the number of actions of each player is finite. An undiscounted epsilon equilibrium is a strategy profile such that no player can benefit by more than epsilon from a unilateral deviation. Namely, the expectation with respect to this strategy sigma epsilon defines the distribution. The expectation of the limits superior of the averages of his payoff is at least what he will get by some unilateral deviation to a strategy sigma I up to an epsilon for any deviation. An open problem, the one that I promised, the dinner plus transportation, is it true that any finite stochastic game has for every epsilon an undiscounted equilibrium? And there are special cases, much work has been done on this work, and special cases are known that this is true. It's stochastic games with perfect information, which are stochastic games, finite stochastic games, where for each state only one player moves. There are irreducible games, which means if you play a family of what's called stationary strategies, then the Markov chain on the state is irreducible. It is true for two-player stochastic games, a deep result, over 100 pages of proofs by VA. It's true for three-player, a subclass of stochastic game called absorbing games, and several classes of quitting games. And now a comment relating a little to soccer. A stochastic game is a discrete time multi-stage game. So we have stages 1 and 1. The analogous continuous time version of a stochastic game has an undiscounted equilibrium. A priori, it looks a more complicated model, but some new features evolve in the continuous time that you could prove this theorem. And this is a result of mine, that any continuous time finite stochastic game has for every epsilon an undiscounted epsilon equilibrium. And another class of games for which we know that this is the case is finite stochastic game with observable mixed action. When you are coming to a stage, you could choose to play top or bottom, let's say, with probability half and half. But the question is, the other player doesn't know that you chose it with probability half and half. He only observes what you actually chose. So in a stochastic game, you'll try to infer from the other of what are the probabilities. But if you are sending these instructions to a referee who discloses it to the other player, these are stochastic games with observable mixed actions. And a forthcoming result is that any finite stochastic game with observable mixed action has for every epsilon an undiscounted epsilon equilibrium. And the results also for classical stochastic game, but now with finitely many states, convex, that's for the mathematicians that are familiar with this concept, convex semi-algebraic action sets and multilinear payoff and transition functions. And I would just finish here with the last slide. The presentation will be on my site, so you can view the details, what is each one of these meanings. These are the three topics that I said. I'm not sure that I'll get to it in the lecture. So there is the asymptotic theory, the uniform theory, and the robust theory, where we look on different concepts. Thank you.